capacitance, I'm talking about linear capacitor, normal capacitor, linear capacitor. So you put a charge of Q on a positive plate, conductor plate, conducting plates. Okay. So you have for Q, on Q, Gauss's law, you get D, from D you get E, from E you get voltage positive, negative, minus integral, minus the plus plate, E dot dl. This is the traditional way of doing it. Then the capacitance is just this, Q upon V plus minus. And the capacitance is a quantity, is a parameter of those plates, which is a capacitor. Zero fringing, this is A, this is B. Zero fringing, epsilon R, then capacitor is epsilon R, epsilon R A upon B. This one we have already derived very well known. But as I told you last week, the linear capacitor, which is passive capacitor, you may have capacitor like Varactor diodes where the capacitor can function on voltage, but this is not our pulse, something else. I teach you. So this is the usual way of calculating capacitance. So today we shall see now, we are looking at electrostatic, electrostatics, the charges do not move, okay. But then on the plate, the charges do not move, but if you apply some voltages on the plate, these charges can move on the plate. So these are the free charges. As I told you, if I have a dielectric, inside here you may create polarization charges. These are the charges inside the dielectric. Polarization, dielectric polarization charges, which do not concern us as far as Gauss's law is concerned, because Gauss's law is integral on the outward flux, Gaussian surface or surfaces, dds simply equal to integral of rho free. Rho is the charge density, Q free. Okay. So the Q free is not here. But the charges inside there are not Q free, they are Q polarization, because these charges there is no way you can apply a current to make them move. You can't. Whereas on the plate, when you apply a current, if you apply a current sideways, you can move on the plate. These are free charges. So in calculating capacitance, you're only looking at the effect of the free charges on the plate, conductor plate, creating the voltage Q over the capacitance. Okay? And we see some cases where you have a concentric capacitor, a power-paid capacitor. We've seen a cylindrical capacitor, coaxial capacitor. This is A. This is B. Conductors are here, obviously, conductor. Dielectrics on R. The capacitor is 2 pi epsilon naught epsilon R over times the length L upon ln. Ln is log E, natural log. You have to know this result because you have to apply it. Then we look at a case where you have capacitance having a split capacitor. Split, say for example, split into two here, same geometry, this is epsilon R1, epsilon R2. So you can see half, you have half, and you effectively have capacitor here C1, okay, is half of that result here, 2 pi epsilon naught R1, non zero here to 0, and C2, the other one here, half 2 pi epsilon naught from R2L at 1 non-zero. The capacitors, these capacitors are in parallel, so basically right parallel because you can see they have a common boundary here. The electric field will be tangential, but the other way is to see that they are the same terminal. This terminal, the voltage is the same, so it's in parallel. So C1 and C2 are in parallel, therefore C equivalent is equal to C1 plus C2. And parallel voltage is common. So we saw that we can have cases where the capacitances are in series. In series, for example, this way. This is conductor, then the dielectric now is in series, the thing is in series, so we have it. This is this one R1. I mentioned to you, this looks like two capacitors in series, C1 and C2 in series, because you can see the voltage across here, from here to here is sum. So like two resistors in series and the voltage together. So in this case, C1 and C2 are in series, that we can. The formula for C1 and C2 we saw already is the inverse of resistors. So the answer is C1, C2 or C1 plus C2. Okay, this is what we discovered last week. So you can see field EM theory gives you some basic result, and the circuit theory makes life much easier when you have the situation get more complicated. So here we make your circuit theory. But the origin, the foundation of circuit theory is electromagnetic theory, is EM principles. Okay? So from this topic, now we finish this topic. We shall look at the tutorial in 1 week's time, 2 weeks' time, to see what we can review. So go to the next topic now, electric current. The electric current here, we're talking about, we shall see, emphasis will be on the steady electric current, steady or DC current. So current, as we know, electric current is a movement of charges in motion. So if the charges do not move, there is no current, obviously. And then we shall see this one, if the charges move, they create a current. You have a current, it creates a magnetic field. Okay. But if it is DC current, it's a DC direct current, you have charges moving there, the charges still have the electric field. The movement of current, steady current gives you a magnetic field. The magnetic field coming from the steady current and the electric field coming out from that bunch of charges moving are not related, they're completely independent. Then later on we shall see when the charges accelerate, go faster, go slower, go faster, go slower, you have formation of EM wave, which is the association of electric field, magnetic field become one. They cannot be dissociated. So at the moment we are looking in general at some concept. Current is charge per second, coulomb per second is ampere. Ampere is coulomb per second. C per second here, coulomb per second. So in general, when we look at this problem, we circuit theory especially, we are looking at the macroscopic view. In other words, actually you have a system, a series of charges moving. Actually, the charges are discrete in that sense. But in a microscopic way, it is discrete, but in a macroscopic way, since the flow is steady, we say that consider the charges moving like a fluid like this, a fluid. Okay. But the microscopic property are the charges move, the point charges, there's some fluctuation in the velocity, especially inside the crystal or some material. So there's some fluctuation. That fluctuation causes some irregularity, which you can see, those of you who know about sharp noise in the harmonic circuit. You see sharp noise, meaning that the things keep on wavering. The thing never straight, it's a random movement. This is just for those of you listening. So now we'll move on to look at current, simple derivation. So we have current. A current is a flow of charges, and in this case here, the current density is the current that goes across cross-section of a conductor divided by the area. Area delta S, then the current density is ampere per meter square, amperes per meter square. Okay. So this is when the conductor is 90 degrees to the S. Now sometimes the conductor may be, you will be taking a surface which is at an angle. In that case, the net current flowing will be the normal component of the current times the area, that is J dot. Yes. In general, delta I J dot product here. Modulus of Z, modulus of area, times cosine angle of the two. As usual. Just like flux, normal flux and normal current. So very soon we shall see that there is a big analogy, similarity between steady current flow and electrostatic problem. Although in a steady current flow, the charges are moving, uniform velocity, uniform. In a static problem, charges don't move, but you will see that we give rise to some parameters which are very similar. So let's look at the simple derivation. Look at this picture here. I have a charge delta Q. So the rho here is the charge density, rho per meter cube times volume, delta V gives you coulombs. This is moving velocity V, this area is A, times T equal to 0 along the z-axis, along x-axis. So at the time delta T away, this thing will move. You can see it has moved the area here. So therefore I can calculate now what has happened, how much current has flown during delta T. So that the delta I current swept through in delta T will be equal to the charge density times the volume, which is, volume here is delta S times delta X. Volume here, delta S here, delta X. So volume, coulomb per meter cube per meter square, meter cube times divided by the delta T per second. So at delta T tends to 0, I have that the amount of current is given by J delta I going is rho V delta S. Okay. So that V here, okay, is the velocity. So I don't want you to confuse with it, velocity. So later we change the notation to, let's call it U rather than V. Okay, let's call it U. Because we use V for volume later on. So let's call it U. U is big velocity, but it's mixed up. Okay. And those of you who do semiconductors know already that the amount of the semiconductor material, the velocity of the, say, particle electron or holes is proportional to the electric field. If you double the electric field, you double the velocity. So the proportionality is called mu, which is the mobility. It's called the mobility. Okay. So therefore, from here you can see rho J is rho times U. Okay. U is mu times E. Therefore, J current density is given by rho charge density per meter cube. Mu mobility times electric field. So rho times mu is known as the conductivity. So therefore, to make things a bit clearer, not to mix up the notation, let me call sigma C. Conductivity C, because otherwise sigma in the thing is charge. Sigma C. I will come back to example next time. So J is sigma C times E. Of course, when we say J is sigma E, of course you know sigma is the conductivity. You don't want to mix up the charge. So this is actually called a point form of Ohm's law. But the Ohm's law that you know is, Ohm's law is current, voltage divided by resistor. This one you know about this, right? So Ohm's law, usual Ohm's law, okay, the current I is V over R, okay, where 1 over R is V and G, conductance. This one you do also get to read. So you can see it's very similar. Voltage is proportional to the electric field, conductance is proportional to conductivity, and I proportional to G. So the consistency is there, which I will show you. So V is equal to IR, IGV, put it the other way, IGV here, G is conductance. So the unit of conductance is the inverse of ohms, okay, ohms. So the sometimes they call it ohm written backward, and it's ohm, and then nowadays they don't use it. I don't know why. Okay. So now you can look at the conductivity, sigma C. Sigma C is 1 over resistivity. You know resistivity is ohm meter, so inverse 1 over. This one is very well known. This one you know already. So all this will do happens. Put a C there to show that it is not charge the conductivity. C means conductivity, conduction. Okay. So we have discovered very interesting one useful law, Ohm's law. It's called Ohm's law in point form. Point form because you can see J denote, for example, J as a function of x, y, z at the point. E denote as a function x, y, z. That's why it's called point form of Ohm's law. Point form means that it is very at the microscopic point. Very useful. But when you say I is V upon R, this is not a point form. This is a macroscopic. This is an overview of the whole system. You are not looking at a point in a resistor. You are looking at a total resistor. You take a resistor, you put a voltage of V across it. Mr. Ohm find out that the current simply equal to V over R. You double the voltage, you double the current for the same resistor, and so on and so forth. Okay. Of course, usual condition temperature will become constant, which you learn in A-level anyway. So, do you have to know this? J is sigma E. Sigma is the conductivity. Now, before we go, I just want to show you a taste of how similar it is. J is sigma E. I put C here, conductivity. And we have seen already that D is epsilon. This is electrostatic, this is conduction current. So you can see there is a similarity. J looks like D, okay, and epsilon appears to be like epsilon. Not equal, but example. And later we shall see that if we know the capacitance of a conductor, we can immediately find the corresponding resistance or conductance of this leaky capacitor. You have a capacitor that's leaky, meaning that the dielectric is not perfect. There is a small amount of conductivity, conductivity. So when you pass a current, in addition to creating a capacitance, you can also create a small resistor, some value. So So let's now look at the next picture. Next picture tells us something about the So this one, you know, those who do semiconductor. You have a conductivity of a semiconductor, you raise the temperature, obviously the conductivity will fall, or the resistivity will increase, because as you raise the temperature, the particle, the electrons, the holes, or whatever it is inside there, they are shaking more and more violently, heating effect, high material gases, therefore you create more resistance to the flow. Therefore, resistivity will go up, or the conductivity will come down. Okay? So I put sigma c here. Okay, and this sigma c is a function of temperature. So that's why I say don't want to mix up rho here, the density. When I put the c there is the resistivity, so density, the charge density. That's why I change the notation, because I have chosen the wrong, not quite distinct notation. Okay? So we saw already that as the temperature decreases, temperature falls, the material gets more and more conductive, and it increases, there's some material called superconductors, which have got infinite conductivity. Okay, as the temperature goes toward absolute zero, absolute scale, minus 273. 0 Kelvin is minus 273 degrees centigrade. And you must have seen some of the picture in the either in YouTube or either in the cinema or documentary, where they show you how if you have, it's a bit like magnetic levitation. You have a magnet, you have a, say, current flowing in a loop, current loop, I, DC current flowing I loop here. And you put a piece of semiconductor, superconductor on top, small ring, whatever it is, something, superconductor. Okay, it floats, levitation floats. Ring floats. This is source of current, source of magnetic field, source of current, I. This one floats. So ring floats. The ring floats over on top of the magnetic field there, because the magnetic field penetrates the ring, and the ring has zero resistance. And the electrons under the influence of the magnetic field will move. They go around non-stop, because the resistance of the superconducting ring is zero, no resistance. So this electron will go on forever, so long as you have a source of current there. Okay? So the electron itself, the ring itself, the current flows inside it, and that current, okay, will create a magnetic field opposite this one. So it will flow. So it will repel. So magnetic levitation. Those of you who've seen a film on Indian fakir, they say they levitate. I don't know. I don't know evidence. They say they can levitate. But of course, there's always a lot of trick. I seen one documentary where this old man in the mountain, of course, he very far away on purpose so people cannot know what's doing. And then to get to his place, to his cave, let's go to all kind of funny obstacle. You're not allowed to film. And then when he wanted to do magnetic levitation, he said he will sit down, put a carpet on his lap, concentrate. If the power is mine, he can float. That's what he says. But he cannot go too near. He cannot go nearer than 4 meters. I'm sure he has some string pulling him up. I don't know. Anyway, all kind of tricks. we're going to see something very important because people normally get confused. Do not confuse the conductor and the steady current flow with the conductor and the electrostatic equilibrium. So let's see the first picture first. I've shown it before. I have a external electric field here, constant, and I put a conductor in it. As I told you, because the conductor, the field will be zero inside. We know that a conductor is a constant potential, equipotential, and a zero field. So therefore, one can explain why there is zero field. The original exterior field is cancelled by the interior field created by the induced charges. This plus 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 is just on the surface of the conductor. Plus minus, this is originally all neutral, so therefore you can see that. Inside here, the E interior plus the E exterior will be zero, you cancel out. So the net field inside the conductor is zero. It's not we know really. The net field inside the conductor is zero. Okay, so this is a good conductor. Under static equilibrium, no current flowing here. Of course, for a fraction of microsecond, the charges will move and then steady. And now look at the case of a conductor in steady state. The conductor in steady state, what happens? How does it look like? Conductor in steady state, I'll change the diagram to make it more comprehensive. This. So if this is a good conductor here, conductivity is sigma C. We know J is sigma C times E. Now it is a mistake to say that the field inside the conductor is zero, because the good conductor is zero. No, it's not. The field inside the conductor is small, okay, but the conductivity is large, so the product J is finite. So a common mistake to say that a good conductor, the field will be zero. It's not. Of course, it's very, very small, and the static equilibrium. But if you connect this thing to a source of DC current, current will flow. Current will flow because the electric field is non-zero. If the field was zero, there will be no current. Because J is sigma C times E. If there is no current, there is no field. I say like that. So therefore, it will be a mistake to say that the current flowing in a good conductor is infinite. No such thing. It's large. Because if the resistor is small, the current flowing is large. But inside the conductor, the product or the conductivity, which is very, very large, times the electricity very small, is finite value. I'll give you the J, current density. That is what is completely a circuit, otherwise the circuit cannot close, cannot move. So when you read books, be careful because sometimes they mistake, are very misleading what they say. So a conductor under in a current, conductor DC current flowing, and electrostatic field are the same. So at the bottom here, simple derivation of Ohm's law. This is surface S, current flowing 90 degrees, so J is at S. Ampere per meter times meter square equals amperes. So this length is L, not inductance, L, length L. Okay. And J is sigma S times ES, you know that. The potential of course is big, we know already. V12 is V1 minus V2, integral minus integral to 1. Okay, so therefore E times L, because 0 minus minus L is equal to L. So the potential here to here is high, this one is higher than this. Again, you can see the current will flow in this direction. Electric field will be in the same direction because sigma C is a scalar. The direction of E dictate direction of J and vice versa. So in this case here, the electric field is going to the right, from the positive charges here, in this way, down here, down here. Okay. So therefore, the current density is I upon S, J sigma is like E, and this one we know already. We know that the electric field is given by V upon L, where V is the potential difference here, V1 and V2, which is sigma C V upon L, or V is L upon sigma S times I, or I. You say Ohm's law, you say Ohm's law. This is the V equal to I, the macroscopic form of Ohm's law. J sigma C is the point form of. So the conductivity is given by 1 upon rho C. I put a C there because it makes a charge. Is 1 upon ohm meter. Resistivity is rho C ohm meter. But of course they have names like Siemens, or they have what the name, conductivity, so many Siemens. Okay. So very simple relationship that we see, beginning to see there is some similarity between the two phenomena, the DC current phenomenon and the electrostatic current phenomenon. In one case, the charges don't move, electrostatic. On the other case, the charges move with velocity to create a direct current. Now we're going to see something very, very interesting, the relationship between the two. R is V over I, V is minus integral 2 to 1 V12 minus integral 2 to 1 E dot dl, as usual, divided by I is integral of J ds dot ds, J is sigma C times E, as usual. C is Q upon V, again, for the same configuration, integral S, D ds, D is epsilon times E, over 2 to 1 E dot dl. So if I multiply them together, you can see the product of RC given by epsilon over sigma C. I multiply them together. Okay? This one cancels. But of course you can see this can only be true provided epsilon and sigma C are constant. Otherwise I cannot take them out of integral. If your sigma C is a function of your S, no way I can remove this outside. So because I'm assuming they're constant, if they're constant, then if they're constant, E dot dl cancel, and then I multiply out. Epsilon is outside, E dot ds, sigma C is outside, E dot ds cancel, give me epsilon and sigma C. This is one way of writing it, but you can see this one is easier to remember. The product of R times C is resistivity C times epsilon. See, R proportional to resistivity, C proportional to epsilon R, so the product you can see is rho C times epsilon. Or if I don't want rho C, epsilon upon sigma C, the same thing. Okay. So therefore now if I give you, we shall see one example, a capacitor which is not perfect. The capacitor has got both epsilon R and also loss, meaning the dielectric is not perfect, has got some conductivity. I'll just show it to you before we look at it. Just one of the following pages. For example, I can give you this capacitor here. You can have a capacitor here. And the capacitor consists of two parallel plates. And the material in between, in the ideal case of the capacitor, the dielectric is perfect, so sigma C will be 0. But now, the dielectric is not perfect, it has a small conductivity. So when you connect a source of DC voltage across it, first the charges accumulate, okay? After a while charge finishing, but there will be a small current flowing. Small current due to the very small current due to the signal C. So this is what is called a lossy capacitor. And all capacitors are lossy. There is no perfect capacitor. That is why you can see this capacitor in your handphone after a while. Your charger, you don't know how many milliamp. After a while you can see the thing just refuse to charge up. Something wrong with it because the capacitor charging, discharging, and so many times. The dielectric is imperfect, it heats up, spoil. Otherwise, how the manufacturer make money? That's why they make cars, they don't last more than 10 years, 12 years. Otherwise, they will go bankrupt. They sell you one car for 50 years, what do they do? Okay, so we look up the options. So in the case of a capacitor, having both capacitance and resistance is possible. But of course, the resistance is very large, very large. Come back to examples. So this relationship has been known, you must remember that. Relationship R and C is rho C times epsilon. So if you know the expression for C, you can find the expression for R. When you make calculation, and vice versa. I will shall show you. And we shall discover also very soon. Yeah. There's another relationship again. When we introduce the concept of inductance, L, C, mu, epsilon. I haven't done it yet. You will see this kind of relationship exists. The product of inductance per unit length times capacitance per unit length is the product of the property of the medium, which is mu, proportion to L and epsilon. So you can see nature has got symmetry. Always, everywhere in the nature has symmetry. Yes, you have matter and antimatter. Antimatter you cannot see. Matter is more, just overrides the body antimatter. Okay, let's go on. So now let's now look at the continuity of current. So remember, a current is a flow of charges. Okay, in the more general case, okay, if you have, say, you have a region where some current is flowing. So if the current density is J, ampere per meter square, and a small element ds, so J dot ds is the current that flows out of here. Okay, so the current may be going in, going out, we don't care. So in general, the net current flowing out of the surface is integral J dot ds of the fluid. So in general, okay, rho is charge density here, not resistivity charge density. dV, the volume, element of volume. Okay, so now let's see this closed surface now. The current is integral J dot ds coming out. Now, if you have a closed surface, current is coming out. So what is creating the current? The current is created by charges changing with time, in general. So somehow, in order for you to obey the conservation of charges, continuity, so much coming out, somewhere somehow will be decreasing. Something is increasing, coming out, something inside it will be decreasing to produce the thing coming out. So the current will be balanced, the outflow current, by the decrease in the charges inside the volume. Surface. Otherwise, something wrong. Charges must be preserved. So the current is minus, look at the minus there, decrease d by dt of rho dV. V is the volume, rho is the charge density, volume density. So therefore, equal to integral of J dot ds minus d by dt of the charge. This is called the continuity equation. Always must hold. Okay, so then first time you meet this, but something you have encountered before. You have encountered before when d by dt go to 0. When d by dt go to 0, this goes to 0. Therefore, integral j dot ds goes to 0. Meaning that the net current flowing into that volume is 0, meaning that whatever current is coming out must be replaced by current going in. This is our well-known Kirchhoff current law. At a node, the node can be a thin node, can be a fat node. The net current coming out, net current going out is 0. In other words, what goes in must come out. What goes in must come out. You know the saying, what goes in must come out. Okay, let's now look at this picture. So you have learned your Kirchhoff current law with a very thin node, but this is also valid for a flat node. The node can be very pointier or can be very low. A flat node or a thin node is always true, provided DC current. Some people already have Kirchhoff current law. You have a node in a circuit, 5 amperes going here. There's one branch coming out, so 5 amperes is coming out. Because it's DC, direct current. But strictly speaking, if you have an RF current coming, changing with time, say 1 milliamps coming in, coming out there is over 1 milliamp. It's different, slightly less. Some of it will be in air, a special kind of current, which Professor Guru will tell you. Displacement current, meaning a special kind of current. Two kinds of current. A conduction current, which flows in a wire, conductor, and a current that cannot flow in a wire, flows in air in a dielectric, called a displacement current. Displacement current. So conduction current, IC, icon, and then a displacement current. Good. So JC, this one related to JC. J is sigma C dot E. You have electric field, you have a sigma C, conductivity. Displacement current, ID is related with derivative of T expected electric field times some constant times the field, or D by D. The D we have discovered in Gauss's law, D is called displacement vector, D, flux density vector. As we know, is epsilon times E. Okay. So the rate of change of this one with time, dd by dt. This is what constitutes your my ID, the current density or the current ID displacement. And this current loves to flow in non-conductors, like air, plastic, whatever it is. Your handphone like this. But it doesn't like to flow conductor because the conductor, the E become very small. Become very, very small. Almost you. So it was that discovery that you need another current when your time changes, that led Maxwell, Mr. James Clerk Maxwell, to formulate the new theory of communication. And we found out that because of this term, because of this displacement current, he is able to predict the formation of waves, electric field, magnetic field being produced. Okay, so it's just a side information. So let's now go on further. So we saw already just now, integral j dot ds, what is it? Yeah, this now we saw. We saw this. Integral j dot ds is minus integral rho dv charge. How it is decreasing with time. By conservation, if we send it to the left, this plus this goes to 0. So this picture is here. But this is an integral form of Gauss's law. An integral form of the continuity equation. So corresponding to every integral law, you have a differential law. So therefore, divergence theorem, if you recall Gauss's law, mass divergence theorem, integral ds minus rho dv, volume, surface integral, volume integral, surface integral, volume integral, give divergence equal to rho. So similarly, continuity equation in point form, in differential form, divergence of j is minus d rho by dt. And you know already divergence, what divergence means. The amount of flow per unit volume coming out of the surface. From definition of divergence mathematics. So you can see from here, the amount of current as flow coming out of the surface must be replaced, must be balanced by the decrease in the charges inside the volume. This is continuity equation. Of course, it is differential form. This one is the integral form, differential form. Let's move further and discover a few of this concept. That's the next picture which I show you now. Some analogy between the capacitance problem and a conduction problem. So we look at the same problem, the same capacitor, but the capacitor here is lossy. Lossy, in other words, let's look at it from a conduction point of view, let's look at it from a dielectric point of view. So you can see. On the left hand side, dielectric material epsilon, right hand side, conductivity sigma c. Left hand side, electrostatic problem. The voltage is given by V0 upon V. On the right hand side, the same thing, V0 upon V. That's Y, changing with time Y. Potential, some potential. Similarly, the electric field, this is constant. Look at the similarity. J is sigma c times E. Okay. Rho S is epsilon times E. Here, rho S is same as D. Gauss's law. Total charge is charge density multiplied by area. Okay. Similarly, total current density times area. You can see sigma c dA, same thing. Here you can see capacitance Q upon V, epsilon A upon D. Conductance is 1 upon I upon G naught, sigma C A upon D. Conductance is 1 over R anyway. So similarly, you can see this picture shows the similarity between them. So the usefulness of this relationship, which we shall see very soon, is that if you have expression for the capacitance, then the corresponding expression for the conductance or resistance can be found easily by using the product. So here, recap here. Epsilon, dielectric property, is similar to the resistivity. I put a C here, because sigma is not the charge, sigma is the conductivity. Q corresponds to the current. You see this relationship. R times C epsilon times rho C, or you can take the other one, the G upon C upon G, because R is 1 upon G, up to whatever you want. This one easier to remember. Okay? And that's a shortcut. For example, this one. So I give you the two plates, having material, having adding constant epsilon R, and conductivity is in C. Add a DC voltage to it. Okay. So it has got capacitance as well as resistance because current is flowing. As I said before, earlier, this is a lossy capacitor. A capacitor is not perfect. That is why all your charger after a while become useless after charging many times because the capacitor inside there charging many cycles, heats up and they away. So now, what is the equivalent circuit of this? You have a lossy capacitor. What would be the equivalent circuit? So I say it is a parallel circuit, C and G. But the question is, it could have been a series circuit. Why is not a series? Why is it parallel circuit? That's our justification. So it is a parallel circuit because if you connect this, you charge up the plate, and then you disconnect the voltage, and you leave it there, leave the capacitor there. This is positive potential, negative potential, there is a current flowing. Okay? So therefore, after a while, this capacitor will be discharged completely. You know, happens in your case, in your handphone. Discharged completely because the current is overflowing. So if for it to discharge, it must be a parallel circuit because here you disconnect sigma C. Capacitor is charged, it's circuited, the current flows here and there. That is why it must be in parallel. But what happens in series? Why it is not in series? If it were in series, the circuit would be like that. Series. Sorry. It will be like this. R, which is charged capacitor C, plus minus, and leave it open. So leave it open. Assuming the air is not conducting, it's going to be there forever. Right? The voltage across the capacitor will be there all the time. Then it will not be discharged. If it were a series circuit, this is a series circuit, there is no path for the current to flow. The current cannot flow in air, cannot flow open circuit, so therefore it cannot be a series circuit. It has to be a parallel circuit, so it's wrong. It must be a parallel circuit, so it's not series. Series connection for equivalent. So for equivalent circuit of a lossy capacitor, you must have a parallel branch there to represent across the capacitor which is charged. Okay, here. Capacitor is charged with voltage V. So it's R also equal G, isn't that the parallel? So once it is charged at a certain voltage, the current is going to flow across the resistor and then becomes zero, decay exponentially. But here no. You charge the capacitor, remove the voltage. If it were series, the charge will always been there, which is nonsense. In physical expectation, you know already physical thing. So capacitor voltage goes to zero, charges will be dissipating. Why? Where did it go? It is flowing across the lossy medium, lossy material. Here in the series connection, it cannot flow. Okay? Okay, alright. So now, suppose now I give you, we've seen already before, a coaxial capacitor. We've seen already. The answer was, we derived by using Gauss's law, 2 pi epsilon naught L upon ln B upon A. This is a capacitor. So if the material had a sigma C conductivity of 1 upon rho C resistivity, what will be the resistance measured? The product in this, you get the resistance. Calculate the R from there. The R will be equal to 1 over, it will log d over A over 2 pi sigma L. All this because, very important assumption, the epsilon and the sigma C are constant. They do not depend on the coordinate system, which in most cases are always like that. In 99% of the cases, it's like this. The properties are constant. Who's going to spend his money and time to go and make the material inhomogeneous? It doesn't make sense. Okay. So I think in the so in this case here you can calculate how long it takes. You have a capacitor which is lossy, you are given sigma C, you have epsilon, you are given capacitor plate and the capacitance, and you are asked the capacitance is charged up, how long does it take for it to discharge? Say to half the voltage. It's a simple capacitor discharge problem. We know exponential T upon tau, and tau is a time constant. You know R, you know C, and everything will be found out, right? No big deal, right? So you have a capacitor with lossy capacitor. You given epsilon R, you given sigma C. Okay. So power of the capacitor, say. So we discharge up, say, to 100 volts. How long does it take to go back to 50 volts? So charge, V max, then V T, capacitor, equals 1 to 50 volts. That's the forward, right? So the simple capacitor is charge, V max. This is going to be discharged to some resistor. So this one has got its own capacitor C, R. So this is I discharge. So IT is simply equal to V max upon R, E minus T upon RC. RC is time constant, it's a simple circuit. You can calculate whatever you have to calculate. And RC, you don't have to calculate RC. If you are given this, you're okay already. You don't need to calculate R. Epsilon naught is on R times rho C. Okay? So you can find what the time constant tau. I said this is the time constant. You are given this. Okay. So therefore this is the same as 1 upon rho C. You can calculate the time constant, tau here. You can calculate when does it become half. Or if you want to be maximum, you want this voltage. Voltage will be decaying exponentially. Can be found. But you can see this is where this comes in. So you don't even have to calculate R, you don't even have to C, because the product you know already. You know the problem in last year's exam and last year's whatever. So you already know what is epsilon R given to you. You already know what is resistivity. So you can find out what's the, you can find anything about the circuit. The circuit discharges from Vmax to something else. That's it. Any questions, anybody? Circuit theory. Okay? So if you are given, so in this case here, so it will be equal to, just do it because 50 equal to 100 E minus T on tau. You know tau, you can find T. if I go one step backward, earlier, I have to write down KVL or KCL inside the circuit and end up with a differential equation, find the answer, which is differential equation. I get the voltage which is decaying, dt Vmax exponential minus t upon tau. Okay. So before we start on a new topic, magnetism, we finish with current. Let me review some of the problems. For example, one of the problems on Gauss's law, which we did not tackle last week. So the problem I want to tackle now is, this is the, I think the example was given to you in a class. The ball of charges the radius of A, the density of rho, rho naught, coulomb per meter cube is a ball, sphere, ball of charges. This is from the lecture notes. You have to find, for example, what is the potential at center C? What is VC upon respect to infinity? And of course, to find voltage potential, I have to go back earlier. To find potential, what do I need? So, I got to go earlier. I need electric field. To get electric field, I need D. To get D, I need Mr. Gauss. For Mr. Gauss, Gauss's law. There you are. So to go from electric field to voltage, center here, okay, I have to have V, say VAB, I have to use VAB, minus is equal to B to A, E dot dl. Because this fellow has got symmetry, therefore this is minus is equal to B to A, dr, dr. Right? So Gauss's law applied to this, but don't forget, potential at a given point P respect to potential AC is respect to infinity. Always, in this case here. So somehow, infinity must be here, infinity must be here. This is by C. So to go to the point C, I must go from infinity. So when I come from infinity, I move towards C along the radius here. I'm covering two regions. I'm covering two regions. R greater than A and R less than A. That's equal to greater than A. Right? So therefore, I have to find R greater than A. What is the electric field? Gauss's law, dr times 4 pi r squared. Gauss's, I'm very far, I'm outside now, outside the ball, R greater than A. I'm outside at this point here. I know the Gaussian surface, radius R. So it is equal to total charge is Q enclosed. And Q enclosed is rho naught multiplied by the volume, 4/3 pi A cube. This is the first range. I will finish it. To reach the point C inside there, I have to go R less than A. So R less than A, I have to find the field on there using Gauss's law, which you already know. Don't forget, I have to draw my Gaussian surface now among the charges, inside the charges. So I draw it in red, just to show you. Brown. Gaussian surface for R less than A. Outside there, Gaussian surface for R greater than A. Done with the So, the second range now we have R less than A, and Gaussian surface here, the radius is R. We have spherical symmetry, again the left hand side is the same. Outward flux coming out of the Gaussian surface multiplied by the area normal over by R squared. Because at a given point R, on this point here, the value of dr doesn't change, so therefore multiplied by 4 by R squared. So if you go to charge enclosed, the charge enclosed is not is rho naught multiplied by the volume contained by these charges. Is 4/3 by R cube. Not A cube, by R cube. Because R cube is the Gaussian surface that I'm looking for. I don't memorize the answer, I look at the thing and I work it out. This kind of problem can be changed, so that unless you understand what you're doing, you're going to fumble. Unless you try to remember, memorize. Where is Mr. Spotter? Mr. Spotter, Mr. Spotter, are you here? You always ask me, you are there. So, I can find the R in this case, and I work it out here. So this one, therefore, this fellow here becomes A to B integral, okay, the C respect to infinity, the same as integral, and do the minus here, minus integral from infinity to C, but infinity is broken into many pieces to A plus integral A to inside there, integral A goes back to R0 to 0. But when I go from A to 0, down here, A to 0, I can substitute the value of dr and substitute for I obtain here the two ranges, and I do integration and I get the answer. This problem is worked out in the tutorial, you have a look. So what you will see is that the potential of the point C at the center respecting infinity is not zero. Is not zero. Because somebody told me, oh, at the center there is zero charge. No, there's no zero charge there. The charge is everywhere. And work it out, you can get the answer. This is done already in the lecture notes. Done for you already. Now, of course, this problem can be modified in many ways. You can have a gap, a void inside there. You can have a void. This problem can be modified. So if you start memorizing, you're dead. So I should say that you're cook. So this problem could have been like that. No. Here there's a hole in the middle. Same problem. What is the potential at the center of the hole or in the hole? Of course, you know that in the hole, potential will be the same. Inside there is no charge. But whatever it is, it can be done. First, following this recipe, you want potential of C respect to infinity. Multiply E in each of the ranges. Here you have 1, 2, 3 ranges. And then either they are three ranges, it so happens that your third range inside there is no field on there. Because when you blow the Dyson surface in the smoke hole there, the charge equals zero. So therefore there is zero field inside there. So therefore the third integral is from infinity to b so this is a, b, okay. So the integral from infinity, so you want the value of the c here. Integral c is with infinity, b c infinity minus infinity to c, and that becomes minus broken into 1 to 3 pieces, infinity to b plus infinity from b to a here, plus integral from a to center c 0. But we say already that this follows 0 because the ER is 0. You can calculate yourself R less than A. Therefore this integral doesn't come. This is done in the tutorial, please have a look. And understand what is going on, what you are doing. Don't memorize solution, no use. You can see that the methodology is the same. You want it potentially before stepping into it. You find a field. To find a field, you must find D first, as I told you. Then find E. How do we do this? Let's find Gauss's law, Mr. Gauss. Assuming you are not forgotten about Gauss's law, obviously. Do this more, 5 minutes more. This is done in the tutorial solution to you, given to you shell. Let me again in 5 minutes, let me go again over this problem of the plates of charges, because again I find out people do things without thinking. The thinking process is missing. So I have, say, two charges, three line charges, minus sigma, plus sigma, minus 5 sigma, whatever. Parallel sheet, as I told you last time we discussed. So the problem is, what is the, calculate the field in the various region. So how many regions are there? 1, 2, 3, 4 regions. Okay. So to do a problem, there are 4 regions. First you must know where you want the field to be. Not there or there. You want one of the points here. Otherwise I keep telling students, you want to go to Ang-Mo-Kio, you don't go to the Clementi station. You must know what you want to do. So in this case here, we're going to make use of the result for a long sheet of charges of sigma. The electric field is normal because it is asymmetric normal, it cannot be anywhere else normal. Sigma. Normal component, En, sigma 1, 2, epsilon, assuming epsilon was there. This is normal to the plate. My plate is this way, and my coordinate system is like that way. X, Y, and Z is coming out. Okay. So there are many ways of doing this problem. So the solution I gave to you, do like this. This negative, the epifield must go this way. Positive, it must come out. Negative, go this way. Negative, go this way. And then I proceed, I use superposition. But what is forgotten is that, for example, if I take a point here, P, I want to find the value EP here. So, there is a field that goes this way. This plays no part, is only come from right and stops there. So this one is not needed. I want a field that goes here. So this one, I want this because by superposition it will go right through. I want this, I want this. I don't want that because it's going the other way, it doesn't come to here. This one actually goes right through here. This one I don't want it, stops there. So I have three things to add up by superposition. No, three, two things. This one, the contribution here. Okay, the contribution to three things. You will do this one here and this one. So am I calling this one positive X or positive AX? So therefore at the point PEP vector, okay, is the same as this, the first one, sigma upon 2 epsilon naught, epsilon. But what is important is that although this is negative charge, here, the fact that I have drawn it this way automatically has treated it as positive already. Otherwise, I've been double counting. Because if I put minus sigma there, put epsilon naught, okay, you can see this is the right. I mean, the field going this way, it's nonsense. So I told you, this is one way of doing it, provided you keep your wits about you. But the other way, which is far simpler, is to do something which is less risky. Call this sigma 1 positive, sigma 2 positive, sigma 3 positive or positive. And therefore all this field positive coming out this way, coming out from it. Don't have to bother. So this one plus X this way. So at this point here, the field is given to the left, so EP using this method. This is for the sigma 1 here, sigma 1, sigma 2, sigma 3, positive. All positive, that is why I draw it this way. So EP is given by, in this case here, minus sigma upon sigma 1 upon 2 epsilon. Assuming it's plus, this way, around minus X. This one, minus, because this goes right through here, is minus sigma 2 upon 2 epsilon. This one goes right through again, minus sigma 3 upon 2 epsilon. Okay? So now I replace sigma 1 by plus sigma 1, no problem. Sigma 2 by, minus sigma. What was given to me here? I replace sigma 2 by plus sigma, replace sigma 3 by minus pi sigma. And then simplify, is the answer. It will coincide with this one if you continue doing it without having the complication of double counting. If you double count, if you put the answer is, the field is minus sigma to epsilon with the negative, you are double counting because by drawing the electric field this way into the negative charge, you are automatically saying that it is minus sigma. I hope you understand it. If you catch this point, you can try and convince yourself. So let's do the top one first. Assuming using this method, so this one is plus sigma, all positive here, plus sigma upon 2 epsilon. Yeah, this one was negative, minus sigma upon 2 epsilon, sigma, so this one. And this one going to the right, plus, because always minus here, plus sigma. So you work it out. 2 epsilon give you 5. same thing. What? This one, sigma epsilon minus sigma 2 epsilon plus 5 sigma. Same. So this one and this one give the same answer, provided you have not do double counting. So when you're doing this problem, you concentrate. You don't iPad on this side, multitasking here. No way. So the same answer. But this one is this easier, safest method because you take all the positive and all the electric field coming out from the charges and take into account the thing and then replace it. Here, you write down the charges negative going into, but then don't forget, when you write here, you cannot put minus there. Double counting. Okay, let's stop here. Please go for your break. Come back at 8:05, 8:04:05, and we can continue with a new topic, magnetism. Please sign your name here.